All right. Um, Continuing on our theme of new stuff, let's talk about a new feature called a macro system. So there's two ways to introduce the idea of macros. On one hand, we could compare macros in other systems like C or Excel, etc., with and try to talk about how to implement them and develop them and make them nice. Another perspective is we could talk about the way in which um, we have always tried to make our kernel language very simple. Very simple. So recall that one of the ideas that we've had is that our language is minimal, minimal, and we implement things in the desugarer if possible. So the idea here is that we want the language that we compile and interpret inside of our VM to be as trivial as possible. That makes it so that it's easier to do it efficiently. It makes it so that it's easier to optimize it and understand it and so on. It also makes it so that it is simpler to understand. Now, that's advantageous, but we could make it even more powerful by trying to make it so that the features that we are implementing in the desugarer could be implemented as libraries instead. So recall, for instance, our whole thing with threads. So threads from class 14 were just in the standard library. Meaning that they could have been made by a user. So anything that could be implemented by a user is somehow inherently better than something that has to be implemented by the language or compiler author, i.e. us. Because there's like an informational problem. Like imagine that you know that you want a feature in your language, but and so you add that to your language. But then I go use your language and I really want a feature, but you didn't add it, and then I'm stuck because I can't implement it in my language. So like let's have like an analogy. So like my language supports numbers, so that's I can write like 2, right? And I can give things names. So I can say like let x equal 2, and I can do addition. So I can write something like let x equals 2, and so I can write something like this. So I can write let x equals 2 and then x plus x. So because my language supports numbers, naming variables, and doing addition, I can write this block of code. But now imagine that I want to do this thing twice. Then I would write let x equals 3, and then I would write plus xx. It's really annoying and tedious to have to write this over and over and over again. It would be really desirable if our language supported functions. So then we could write something like let double x equals x plus x, and then I could write double 2 plus double 6. And then now, because I've added the feature in my language of defining functions, I've now made it so my program can be drastically simpler. So every time we increase the level of abstraction available in our language, we make it more pleasant to write more programs. Simply having numbers in addition, plus 2, 2, is very tedious. So instead we add variables, but even variables is tedious compared to having functions. And what this means is that I don't need to like call up the author of my language and say, please implement the double function so I can have that. I have the ability to add whatever functions I want. So taking that same perspective, it's great that our language supports people implementing threads in the standard like in user code, because that means if we didn't include it in the standard library, they could implement it themselves. Now, so many of the features of our language are implemented inside of the desugarer. And in fact, they can only be implemented in the desugarer. So let's take an example of one of them, like let. So we have this rule in our desugarer that says desugar, if you have a let, and you have some variable name xe, we just have equal, and then some expression in b, we want that to go to a lambda with x, b, and we're going to call that with xe. Okay, so that rule inside of our desugarer is a very valuable rule because it gives us lets. We would have to otherwise write this thing ourselves. We'd have to write, let x inside of plus xx 2, rather than writing let x equal 2 and x plus x. Okay? So this is way more pleasant than writing that. Now, this thing that we're adding in our desugarer, would it have been possible to implement this in our standard library using the tools of our language? Could I write a function that looked like this? Could we write define let x xe b that goes to lambda x xe b xe? Does that make sense? Would it make sense to then write the following? Let x2 inside of plus xx. The answer is no, this doesn't make sense, because this right here is a function call, which means that we're going to look at let, see it's a function, find that function. We're going to see this x right here. That's an expression. We're going to try to evaluate it to a value, and it's going to get unbound, because it's an unbound variable. And then we're going to go over here, and this is going to be unbound too. So the thing is that this thing right here is not a program, because it has free variables. The thing that functions cannot do is they cannot introduce binding forms. Functions cannot introduce binding forms. When I say binding forms, I mean program syntax that introduces names. And that's because functions always operate on values. Similarly, so functions always operate on values. So that means when you call a function, every piece of it has to be reducible to a value, and it's that value that actually gets looked at. Okay. So what's an alternative? Well, what we could do is we can imagine that this desugarer rule right here, we can imagine that let's just put that into our language itself. Meaning that, like, we could imagine that there was a form in our language that was called extend the desugarer. And we would pass in let x xe b, and we would say that that form will get translated to lambda x b xe. And if we just added the feature extend the desugarer in our language, then we could just define this as meaning take the desugarer and add that rule to it. This is extremely similar to the way that macros work in a language like C. So recall in a language like C, you can write something like define max xy, and then we could write x greater than y, question x otherwise y. So we can write that in in C. Don't want this colon at the end. Okay? Then in our programs, you could write something like max 3, 4, and then that is going to be turned into 3 greater than 4, question mark 3, colon 4. Okay? And you can use this textual substitution feature, so C, textual substitution, to introduce binding forms. So we could write something like define temp x, and we could write, auto temp equal x. And then in my program, I could write something like, temp 3. Then I could write return temp plus 2, and then this gets turned into auto temp equals 3, return temp plus 2, and this program compiles perfectly fine because temp right here is allowed to introduce names. And similarly, I could write a macro like define let x xe, and it would be auto x equals xe. Then I could write let x be equal to 3, let y be equal to 4, then I could write return x plus y, and this would get converted to auto x equals 3, auto y equals 4, return x plus y. Okay? So these are all things that you can do with C macros. And notice that C macros allow us to introduce names, they allow us to use names, and they allow us to, do purely textual substitution like this. So there's some precedent for something like extending the desugarer. However, the problem with C macros is their textual substitution has big fundamental problems. For example, what would happen if we wrote the following? What would happen if we wrote max of 1 plus 2, 3? Well, that's going to get converted to the following. It's going to get converted to 1 plus 2 greater than 3, question mark 1 plus 2, colon 3. Okay? Now, the interesting thing about this is that the way that this is going to get parenthesized is as the following. It's going to get parenthesized like this. Okay? Meaning that we're going to do is 2 greater than 3. It's not, so return 3. And then we're going to add 1 and 3 together. So this right here is going to return 4, which is not what you expected. Similarly, if I did something like 2 times this, then that's going to expand to 2 times that, which is going to get parenthesized like this. So it's going to be 2 times 1 plus 2 plus 2, you know what I mean? So it's crazy, right? The thing is that because C macros are textual substitution, they don't respect the expression structure of the language. So what that means is if you're going to use C macros, you have to be extremely careful about that, and you would have to write the max macro like this. You'd have to write it as parenthesis x greater than parenthesis y question mark parenthesis x colon parenthesis y parenthesis. And so you have to be really careful to make sure that your macro enforces the expression structure that you hope to attain. It doesn't happen automatically. Furthermore, one of the problems with C macros is that it's not possible to make them safe for effects. So what do I mean by that? What I mean by that is that imagine we write the following: max of I plus plus 3. What's the problem with this? It's going to be turned into I plus plus, and we can imagine that we did the correctly parenthesized one, greater than 3, colon, I plus plus, colon 3. Okay, now what's the problem with this? The problem is that I plus plus happens twice. Okay, so how can you fix that? Well, what you might try to do is you might try to do something like define max of xy is equal to a brace of auto temp x equals x, auto temp y equals y, and then return x greater than y, colon x, y, question colon y. Now the problem with this is that this return is not going to return from these parentheses, it's going to return from the whole function. There's no way inside of C to bind a name and then use those values and have the value pop out the other side. Basically, there's no corresponding thing like a let expression inside of C. So C macros are broken in lots of ways. They're broken because they're purely textual substitution. They don't express the expression rules of the language. They don't even express the tokenization rules of the language. Furthermore, they don't, like C itself is not expressive enough to allow you to do things like naming, which makes it so you can't use macros effectively for that. All right. So it would be nice if we could solve these problems and have a feature like extend the desugarer that didn't have those problems and worked. So this is what Lisp-style macros do. So Lisp, scheme, racket, macros solve these problems. And the feature is called define syntax rules. That's what it's actually called in these languages. So let me write a real example of how this works. So if we were to write define syntax rules, and then we have an open parenthesis, let, open parenthesis, bracket, x, xe, dot, 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 close that, be, close that, and then over here we write lambda, x, dot, 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 be, close parenthesis, xe, dot, dot, dot. Then this right here is the real actual syntax that is supported in Racket for extending the desugarer for Racket to support the let rule. Then when you wrote something like let x be 2, y be 3, plus, that's supposed to be a plus xy, this is going to expand into lambda xy plus xy 2, 3. So these dot dot dots here are literally the syntax that you actually write inside of Racket to use the define syntax rules feature. So let's talk about how this works. So first of all, actually there's one more thing about define syntax rules, that there can be many different cases, so these parts right here would themselves be inside of brackets, because you might have multiple different cases. So here's an example of multiple cases. we could do define syntax rules, and we'll say if you have or all by itself, then it will expand into false. Yes, false. But if you have an or with an x and then y dot dot dot, then this is going to expand to let temp of x if temp otherwise or y dot dot dot. Close the if, close the let, close that case, close that. Another example might be for defining and. Define syntax rules. An and all by itself would be true. And an and with one thing, x, would just be that thing. And then an and with more than one thing would be if x and y dot dot dot, otherwise false. Close the bracket, close the define. So each one of these things is called a pattern case. This part right here on the left is called the pattern. And this part right here is called the template. Okay, so one set of syntax rules has many pattern cases, also called clauses. And then each clause has a pattern and a template. All right. And I guess one more thing that I want to say is that the first thing in each of the patterns, right here, and right here, so all of those things are the macro name. Okay, so the name of this macro is and, the name of this macro is or, the name of this macro is let, so on. Okay, so here's the way that it works. Define syntax rules takes the name of the macro and it takes a list made up of pairs of a pattern and a template. Okay? Now, as I mentioned, the reason that we know what the identifier is of the macro is because each pattern starts off with that. Okay? So, for example, the let macro, it would be let is the name of the identifier, and then there's a list, and then that has inside of it the pattern, which would be let x xe dot 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 be, and then the template would be lambda x be. Sorry, there should be a dot 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 there. Let me erase. X dot 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 be xe dot dot dot. Close this parenthesis, close the pair, close the list. Okay? So define syntax rules has these two pieces, the name and then the patterns. And then what's going to happen is that our desugarer is going to see define syntax rules, and it's going to add these to a little database that it has. It has a little database of all the different defined syntax rules or macros that's been defined. So desugarer will track a database of macros, i.e. a mapping from identifiers, from macro identifiers, to a list of a pair of a pattern and a template. Okay? Now, at the end of our desugar, we're going to add one single case that's going to say, what if there is an identifier and then some more stuff? And we're going to have this macro database. Let's just move this. Let's have a macro database that we'll call capital M. And we'll say where M is inside of big M, meaning that this right here is inside of our macro database. In that case, what we're going to do is we're going to call expand on the definition of the macro with its use. And its use is M more ... And so now let's talk about this expand function. Overall, the job of expand, when we call expand and we give it some example code like let x be equal to 2 inside of plus xx, okay? So I gotta swap that. That's going to be the second argument. Let's see if this works. All right. Let's just modify this a little bit. We don't need that part. We don't need that part. All right. Okay, so expand is going to be called with the definition of the let macro and this instance of it being used. This right here is the definition, and this right here is the use. Okay, and expand's job is to take the definition of the use, and it's going to return lambda x. Actually, you know what? I'm going to modify the use to not use x. So it's clear to you that it doesn't have to be x. Let's call it z. ZZ. Okay, so it's going to say let z inside of plus ZZ, and it's going to call that function with 2. Okay? So expand's job is to take the definition and the use and expand that. So how does it work? Here's how it's going to work. There are going to be two functions. The first one is going to be called pattern match. So let's just call it match. So it's going to be called match. So what match is going to do is it's going to take a pattern and an S expression, and it is going to return false or an environment. And what an environment is a mapping from identifiers to S expressions. And then there's going to be another function that's called transcribe. And what it's going to do is it's going to take a template, and an environment, and it's going to return an S expression. Recall that this part right here is a pattern, and this part right here is a template. what expand is going to do is it's going to call match with each pattern and the use until match returns an environment. So it's going to go through this list, and whatever the first one that actually returns an environment, it's going to move on. Then it's going to take the environment that comes back and call transcribe with the template and with the environment. So what I mean by that is that what's going to happen is that with this use right here, I'm really excited about copying stuff. So let's do that again. All right, so let's copy that, and we'll go to the next page. Plop it right there. Okay. Right again. So we are on 16.9. Okay. So with this use, what we're going to do is we're going to call match, and we're going to give it the pattern, which is let x, xe, ... be, and we're going to give it the use, which is let z2 plus zz. And what it's going to do is it's going to return an environment. I will explain how it does this in a moment, but let's just write down what environment it returns. The environment it returns is going to be, it's going to say that x goes to the list z, and xe goes to the list 2, and be goes to the expression plus zz. So notice that what it did is it took this pattern and looked at the corresponding use and matched the various pieces. So x matched with z, xe matched with 2, and there were many of those, so that's why it got put in the list. Be got matched up with the plus zz. Okay? Then what's going to happen is that we're going to call transcribe, and we're going to give it the template, which is lambda x ... be xe ... and we're going to give it this template right here. Sorry, this environment right here. And what it's going to return is it's going to return lambda z plus zz 2. So notice that what it did is it found this x right here and replaced it with with z, because that's what the template said. So that's what the environment said. It's going to find this be and replace it with plus zz, because that's what the environment said. It's going to find this xe and replace it with 2, because that's what the environment said. All right? This is a very simple system, but it has some pretty useful rules. Sorry, it's a very simple system, but if you piece it all together, it has some really cool consequences. So let's write down how it works. So the match function, if the pattern is empty and the use is empty, then it's going to return an empty environment. If you call match and you gave it a cons of a pattern A and a pattern D, so this means a list, and there was also a cons of a use A and a use D, then this is going to be equal to calling match on the left side of the pattern and the left side of the use, and then merging that with calling match on the right side of the pattern and the right side of the use. If you call match and you were given a variable x and you were given any use u, then what we're going to do is we're going to say that we're going to map x to u. And if we call match on a constant, n, and we're given an n, then we're going to return empty also. Now there's one more rule that we need to do, which is that if we call match and we're given a list where we have any pattern and then literally ... then what that's going to do is we're going to call a function called merge on calling map of calling m on the pattern on whatever the use was, u. So the idea here is that we're going to assume that u is a list, map over it, meaning that we're going to call this function on each thing, and then that's going to come back with a list of environments, and we're going to merge them all together. And what it means to merge them together is that we're going to, like each one is going to say x is 2 or x is 3, and then we'll combine that into a single x that says that it's a list of 2 and 3. All right, so now we can talk about transcribe. So transcribe, when we call transcribe and we give it the empty template and an environment, we're just going to return the empty s expression. When we call transcribe and we have a cons of a template A and a template D in some environment, then we're just going to call cons on calling transcribe with the template A and the environment, and transcribe the templates D and the environment. If we call transcribe on a variable x, then that's just going to equal, in the environment, and that's going to just look up in the environment what the variable x is. And if we call transcribe on a constant, n, in some environment, then we'll just return that constant. Constants, by the way, are things like numbers, strings, that kind of thing. Now the last thing that we need to do is for the ... Ooh, I'm going to be crazy. Watch this. We're going to move everything slightly up. I think that's giving me enough space. All right. So then when we call transcribe on a list that has some template and then ... in some environment, then what we're going to do is we're going to call map on transcribing the template, and then we're going to call unmerge on the environment. And basically what unmerge is going to do is unmerge is going to take something that says that x is a list of 2 and 3 and turn it into two things, where two environments where one says x is 2 and the other one says x is 3. So it's going to do the opposite of merge. And this right here is all we need to know to implement this feature. All right. Now, there's one more thing about syntax rules that is very useful, which you don't have to implement, but real systems do it. And that will be shown if we go and look at the OR macro again. So recall the OR macro basically says, so we'll write it out, define syntax rule, OR with nothing is just false, and then OR of x, y, ... is let temp x be if temp or y ... Close the if, close the let, close the clause, close the define syntax rules. So now let's look at an example of using this. So imagine that we wrote let temp be 4, and we write or false temp. This is going to expand to the following. It's going to expand to let temp be 4. That's from the outside. Now we're going to expand the let macro, so we're going to have let temp be x, which is false. Then it's going to say if temp, right? Actually, let me add one more case here. We'll have another case that says or x just goes to x. If temp, then it's going to say or y dot dot dot, which is just or temp, so therefore that's just going to be temp. Close this if, close the let, close the let. Now, if we run this program, what is it going to evaluate to? If we run this program, it's going to evaluate to false. But if we look at this, we expect it to evaluate to 4, because we expect or false to be equal to the other thing, which is just 4. The problem, of course, is that using this let right here has taken over the name temp. So this is called capture. And by default, Lisp macros do capture like this. And this was considered a big problem when people discovered this problem. Now, the scheme community came up with a solution for this. Intuitively, the idea is that we want this temp right here to be attached to these two things, whereas we want this temp to be attached to that thing right there. And so how can we enforce that? Here's the intuition. The intuition is that we want to make it so that this temp right here is somehow labeled. So let's call it like temp 0, and this will be temp 0. And up here, this will be temp 1, and that's temp 1, and that's temp 1. Now when we expand, we have 0, 1, 1, 1, 0, and then they're all distinct from one another. And thus, it matches what we expect. These little zeros in right here, we call them timestamps. Timestamps. And people came up with an idea for how to generate and check these timestamps. However, it turns out that timestamps alone were not sufficient. So the next idea that people had, and basically the reason why they're not sufficient is because what if we use the OR macro twice? And if we use it twice, then that means that we now have 2 different instances of temp 1, and so we want to make sure that those don't overlap with one another. So this idea came out that's called coloring. And basically the idea of coloring, so capture turned into timestamps, turned into colors. And the idea of coloring is that imagine I take your program and I paint it green. Now the entire program is green, meaning that define syntax rules is green, that temp is green, that temp is green. Everything's green. Okay. Now if we just follow the normal expansion rule, now this whole program will be green. But here's what we do next. The next thing that we do is that every time we are about to do an expansion, I'm going to paint the body of the use a new color. Let's say I'm going to paint it red. So now the whole program's green, except that this part right here is also red. It's green and red. Then what I do is I do this expansion step. In this X right here, it is painted green and red. So that means that this X is green and red, which means that that is green and red, and this is green and red. Okay? Then what I do is after I generate the template, I paint what comes out anti-red. Now what is anti-red? How anti-red works is that if you paint something that's red, anti-red, it becomes not red anymore. But if you paint something that's not red, anti-red, it becomes red. Okay, so what does that mean? That means that now this let right here used to not be red, and so now it becomes red because I painted it with anti-red. So that means that let, temp, and 4, they're both green. That false is green. This temp right here is green. But let, temp, if, temp, and temp, those are all red. And so that means that these things match each other because they are red. Well, they're red and green. And these ones match each other because they're only green. Okay? Now, there's a little bit more to the color story that's more complicated, but the way that I've described it was a later theory called sets of scopes. And if you Google Matthew Flat, sets of scopes, then you will find a very interesting talk where he explains this in a very simple way with tons and tons of pictures about how it works. But essentially what this does is it makes it so that rules like this will automatically not have any, they won't take over people, they won't take over names. We call a system like this a hygienic macro system. Hygienic, of course, meaning clean. And of course, people who don't use a macro system like this are dirty, and do you want to be clean or dirty? All right. The story of macros is much, much more complicated than this. There's more that we could add than just define syntax rules, than just hygiene. There's all sorts of features. One of the main things that makes the Racket language special is that we've added lots and lots of things like this. We've added ways to do evaluation at compile time. We've added ways for macros to communicate with one another and to store invariant information. There's a huge world to go deeper into macros if you wanted to, but this is enough for now. All right. Sounds good. Talk to you next time.